Hello there and welcome to my channel on chemistry lessons. Please make sure you like and subscribe to make sure that you don't miss out on any future content that's going to be uploaded. So this video is going to look at how we construct Born Haber cycles, and towards the end of the video you're going to see some past exam questions including calculations associated with Born Haber cycles. If you haven't already looked at the definitions video, which is before this, make sure you do, because you must be super confident with your thermodynamic definitions before we can construct these cycles. Let's jump straight in and have a look at how we would go about constructing a Born Haber cycle. So the first place I would start would be to have the elements and 1 mole of the ionic substance on the bottom line and have the elements in their standard state slightly above. And that allows us to mark on our cycle the enthalpy of formation. Now this is the enthalpy of formation, not lattice formation. You need to be confident they are definitely different things. So here I've shown the enthalpy formation being negative. It usually is. However, occasionally you might see it being positive. If it was a positive change, we would show the ionic lattice above. Okay, because what we see here is a scale in enthalpy. So movement downwards is showing exothermic and the movement up over would be endothermic. The next thing I would do is I would have my gaseous ions. And this now allows us to show on our cycle the lattice enthalpy of formation. So we go from the gaseous ions to 1 mole of ionic lattice. That is the enthalpy lattice formation. Now what we need to do is complete this as a cycle. So we need to make a link now. We need to somehow get from the elements in their standard states all the way to gaseous ions. So what we're effectively doing is going from elements to gaseous to then ions. Okay, and we'll see step by step. So usually what we would do next is we would atomize the metal. So you can see here what I've got now is, instead of just having elements, so one of the elements would be a metal, one of the elements would be a non-metal to form our ionic lattice in the formation. Moving up over, if we atomize the metal first and we have left the non-metal as an element. So we've atomized the metal and then we would atomize the non-metal to just get gaseous atoms. So we've atomized the metal, then atomized the non-metal. So we've gone from elements to atoms in 2 steps. Once for the metal, once for the non-metal. These could be either way around. We could choose to atomize the non-metal first and then atomize the metal. Doesn't matter which way around. Also be careful here, because when you atomize a non-metal, we could be given enthalpy of atomization, or we could be given some bond enthalpies. And you'll see why that makes a difference in a moment when we look at some specific cycles, because this is a very general cycle now. So what we've got gaseous atoms. We now need these gaseous atoms to become gaseous ions. In other words, we're going to be taking electrons off the metal to make positive metal ions. Then we're going to put these electrons on the non-metal to make negative ions. And then we'll have our gaseous ions. So we'll go through, first of all, we'll take the electrons off, which is ionization energy. And then what we'll do is we'll take these electrons and put them on the non-metals, which is electron affinity. And that now gives us our gaseous ions, and we have a complete cycle. That's a very, very general Born Haber cycle. I'll just take this opportunity to point out that don't be concerned if we are given or asked about lattice dissociation. The only difference it's going to make to the cycle is the arrow would point from the ionic lattice up to the gaseous ions. It would become a positive endothermic process as opposed to the exothermic process. Okay, numerically it will be the same. So just be aware of the difference between lattice dissociation and lattice formation. Okay. And again, you should be super confident on the values of the other arrows. For example, that ionization of the gaseous atoms to be gaseous metal ions, that's always going to be a positive change. It's always going to be an upwards arrow. And likewise, the first electron affinity will always be a downwards arrow. Okay, so we must be confident on the exothermic and endothermic processes. Also, I did point out that we could atomize the metal first or the non-metal. It doesn't matter which way around you do it. Okay, so they can happen in either order. Let's have a look at a specific Born Haber cycle then. So this is going to be a Born Haber cycle for calcium bromide. So let's have the elements in their standard states under standard conditions. So that's going to be 1 mole of calcium solid metal and 1 mole of Br2 liquid. Okay, so that would then form an equation for the enthalpy of formation would be Ca solid plus Br2 liquid goes to Ca Br2 solid. That would be an equation for the enthalpy of formation. Then let's go across and do an equation for the lattice formation. So in this case, it will be 1 mole of calcium 2 plus gaseous ions and 2 moles of Br minus gaseous ions. And that would show the lattice enthalpy of formation. So now what we need to do is complete this cycle. So we're going to undergo atomization first, and it doesn't matter whether I choose to atomize the metal or the non-metal first, and you've got to be comfortable with this because exam questions may change these over, and if you've only looked at one, then you are going to be concerned in an exam if it's not the exact same one that you've seen. So in this case, I have atomized the metal first. So there's the enthalpy atomization of calcium, and it's only 1 mole because we are atomizing 1 mole. Then we're going to undergo either twice the atomization of bromine, because it's twice the atomization because I'm forming 2 moles of bromium gaseous atoms. Or it could be the bond enthalpy of bromine, because if you construct an equation for the bond enthalpy of bromine, it will be Br2 forms 2Br. So it's 1 times the bond enthalpy, because the bond enthalpy breaks 1 mole of bonds to make 2 moles of atoms. Or it's 2 times the atomization, because the 1 atomization only forms 1 mole. Got to be careful there and make sure you understand that step. Ask questions of your teachers or myself if you don't understand that step, and we'll clarify it. Next, we need to undergo ionization. We've got our gaseous atoms now, but we want our gaseous atoms to become gaseous ions. Now I have to atomize the calcium first, because I need to take the electrons off before I can put them on the bromine. So I'm going to do the first ionization energy, and it's only 1 times the first ionization energy because it's only 1 mole of calcium ions. Then I need to do the second ionization energy of calcium, because I need to remove that second electron to make it 2+. The final thing I'm going to do is going to be the first electron affinity of bromine, but notice how it's 2 times the first electron affinity of bromine, because what I'm doing is I'm adding 1 electron to each of the bromines. I'm adding 1 electron to one bromine and 1 electron to the other bromine. I am making 2 moles of bromide ions, so it's 2 times the first electron affinity. What I'm going to suggest you do is I'm going to suggest that you have a go at constructing your own for sodium oxide. So I suggest you pause the video and you try and construct your own cycle, and then when you're ready, unpause, and I'll quickly whiz through this one and see if yours matches the one that I've done. Okay, so again, my advice would be to have your elements on a line just above and show the enthalpy of formation. Notice how it's a half O2 gas, it's not O2 or O. It has to be oxygen in its standard state, which is O2, and we only need 1 oxygen atom, so it's a half O2, and it's 2 sodium solids. Then we have our gaseous ions, which in this case is 2 moles of sodium ions and 1 mole of O2 minus ions, and that's our lattice formation. Next, this time, just to be awkward, I've chosen to atomize the non-metal first, which is either the atomization of oxygen to form 1 mole of gaseous oxygen atoms, or half times the bond enthalpy, because the bond enthalpy of 1 oxygen molecule would make 2 oxygen atoms, so I need half the bond enthalpy. Next, I need to atomize the sodium, and it's 2 times the atomization of sodium because I'm forming 2 moles of sodium atoms. Then it's 2 times the first ionization energy of sodium because I'm forming 2 moles of sodium plus 1 ions. Notice how the electrons are also in the equation. That's essential. That plus 2e minus must be on that top line. And then the final step is to show the electron affinity. But we need to do it in two stages, because we need to put both electrons on the same oxygen. So it's not 2 times the first electron affinity. It's the first electron affinity to put the first electron on, and that's a negative change. The second step is to put the second electron on. So we're doing the first electron affinity to make O minus. We're then doing the second electron affinity to make O2 minus. And that second electron affinity is positive. We saw it in the previous video because there's a repulsion between the electron and the negative O minus to overcome. So it's a repulsive charge there to overcome. Okay, let's take a look at a real past question then. So if you're feeling up to it, pause the video. This should take you in the region of 4 to 5 minutes. So have a pause of the video, try and do the question yourself. And when you're ready to hear the answers, unpause. Okay, so the first thing we're asked to do is to complete the Born Haber cycle. So, as expected, we've got our 1 mole of ionic lattice on the bottom. So what I'd expect to see on the line just above would be the elements in their standard state. Now the standard is going to be cesium and iodine. Now iodine is I2 and it's a solid. You should be aware that iodine is a grey solid. Cesium is going to be a metal and also solid. Now it's not quite balanced. I need half I2 because there's only 1 iodine atom or ion in CSI. And finally, the top row needs to be done. So the top row is going to be our metal gaseous ion. In this case, it's a +1 ion because it's in group 1. We must put the electron in there to show the electron's being removed, and the iodine will still just be a gaseous atom at this point. So must have state symbols, must have the electron on that top row. Okay, there's 1 mark for each correct row. 2 marks. Now we've been asked to do a calculation. We've not looked at any calculations so far. We've only looked at the construction of cycles. So let's have a look. What I'm going to do is I'm going to take each one of these values from the table and I'm going to put it alongside one of the arrows. So enthalpy atomization of cesium. That arrow will be this one. So the atomization of cesium, this is 79 right here. And it's only 1 mole, so I'll leave it just as 79. It's 1 times 79. The next arrow is either the atomization of iodine or half the bond enthalpy. And this is where I've got to look at what I've been given here. Okay, I have been given, where is it? In fact, actually, that is what I've been asked to calculate. That is my unknown. I've been asked to calculate the atomization of iodine. The next value in the table, the first ionization energy of cesium. The first ionization energy of cesium is the arrow at the very top. And that value there is 376. And again, it's for 1 mole. I'm happy that it's just 1 times 376. The next arrow coming down is the electron affinity of iodine. And in this case, it's -314. I expected it to be negative, and it is. And the enthalpy of lattice formation is -585. That's this value. And then we've got the enthalpy formation, -337. Do not get those the wrong way around. It's important that we know the difference. So what do we do now? I'm going to change my color so it stands out a little bit more. Our unknown is X. This is what we're trying to find out, our X value. So what I would suggest you do is almost like you did with your Born Haber cycles, or sorry, your Hess cycles in first year. I'd have a start and a finish. So that's my root 1, like this. There we go. That's what I'm trying to find, which is X. Root 2 is just the opposite way around. So instead of going from start to finish this way, I'm going to go the other way around. So I'm going to go down here, then down here. So this is -79 for the first arrow coming down here. Then it's -337. Now I have to come up here. So this is now +585. Then I have to come up here and that's plus 314. And then I have to come down here, and I'm at the finish line. Now down is minus 376. So because this scale, up is a positive, down is a negative, so I'm very confident that I've got these the correct way around. So minus 79 because I was coming down against this arrow, minus 337 because I was coming down again, plus 585, plus 314, minus 376. Work that out on your calculator and you get a value of plus 107. And this is where I can check, does that seem realistic? Yes, I'm expecting a positive value. My value here is plus 107. That gains me 2 marks. Okay, let's look at one more question then. So again, I would pause the video now and I would have a go at this yourself. And then when you're ready to hear the answers, unpause the video. Okay, so we're asked first of all to complete the missing cycle. There are 3 blank lines and therefore 3 marks. Okay, so what's happening here then? We've got the elements here as expected. We've got one more of the ionic lattice here as expected. They have opted to do the atomization of the non-metal first. That's fine. And then they've done the atomization of the metal. So the next step has to be the first ionization of magnesium, because we must take the electrons off before we can put them on the oxygen. And we have to do the first followed by the second. We must have the electrons in there too. Okay, so no other answers are accepted. Next we have the first electron affinity. So we put one of the electrons, leaving us one left. Put one of the electrons on the oxygen to make it -1, and then you can see what's happened at the final step is they've put the second electron on to make O2-. So there are no other correct answers. You must have the state symbols, you must have the correct number of electrons for each one. Okay, calculation then. So what I'm going to do is take the values, I'm going to show them on the cycle. So enthalpy formation of magnesium oxide is -602, that's right there. Then we have the enthalpy of atomization for magnesium, and it's just one of them. That value goes here. That's the atomization of magnesium. Then we've got the atomization, no we don't, we've got the ionization of magnesium. So that's the first one here, that's 7, it's right there, 736. Then we've got the second, which is 1450. And then we've been given the bond dissociation. Right, so this is the one I've said you've always got to look out for. The non-metal. Is it bond dissociation you've been given, or is it atomization? Now it's bond dissociation. Now here you are breaking half a mole of bonds. So this has to be a half times 496. Got to be so comfortable on the different definitions, bond dissociation or atomization, because that is half the bond enthalpy, or it's 1 times the atomization. Got to be so comfortable there. Moving on, the first electron affinity is -142. Second electron affinity is +844. And I've been asked to calculate the lattice formation. That's this value here. So I'm going to change the colour. We've got our start and our finish. So this is our unknown x, and x is going to be equal to, so root 1 is this way. Root 2, I have to come the other way. So root 2, I'm going down here, which is -844. Then I'm going up here, which is +142. Then I'm coming down here, which is -1450. Then down here, which is -736. Then I'm coming down here, -150. Then down again, which is -1/2 times 496. And then finally, the last step is down here, -602. Punch all that in your calculator and you get a final answer of 3888 minus 3888. And that's worth all 3 marks. And that brings this video to a close. Quite a long one, but Born Haber Cycles is a guaranteed question in your A-level chemistry paper. It's definitely worth making sure you can do the calculations and you can construct cycles. Any questions, use the comments. If you think there's any other videos you'd quite like, let me know. Make sure you check out the definitions video and make sure you check out the next video, which is going to look at the perfect ionic model. Good luck.